Now you will see what are the types of the semiconductors. Okay, entire our subject is based on the semiconductors only. Now we have understood some concept regarding the semiconductor, and successive of that one we have to see what are the types of the semiconductors. So two types are there. Those are pure semiconductor, and second one is impure semiconductor. Okay, pure semiconductor, impure semiconductor. So pure semiconductor can also be called as intrinsic semiconductor, and impure semiconductor can be called as extrinsic semiconductor. Okay, and to fabricate the electronic devices such as diode and transistor, we are going to use this impure semiconductors only or extrinsic semiconductors only, not by using the intrinsic semiconductor. So intrinsic semiconductor is nothing but directly available semiconductors. Those are like silicon and germanium. Silicon and germanium are pure semiconductors or intrinsic semiconductors. These are not enough to fabricate or to create our electronic devices like PN junction diode. So what is required now to create the electronic devices is nothing but extrinsic semiconductors only. And here these extrinsic semiconductors are of two types again. One is N-type extrinsic semiconductor, second one is P-type extrinsic semiconductor. You can say PN diode. So one P-type material is required, one N-type material is required, so that you can create the PN junction diode. So anyhow, before entering into the diode, you need to know what are the intrinsic and extrinsic semiconductors. Okay, now we'll start with the intrinsic semiconductor. So as I said, these are directly available semiconductors. Examples are silicon and germanium. Intrinsic semiconductor. Intrinsic semiconductor like silicon. Okay. So if you take energy band diagram of the silicon, so here energy you will take in the electron volts, so don't forget that one. We have valency band and here conduction band. Okay. Here energy levels with electrons are available. Okay. These are now bounded electrons. But when you apply the temperature, these bonded electrons will go to the conduction band. This is what is happening because of the increment in the temperature. So, can you tell in number, what is the relation between number of free electrons generated here with respect to number of holes created here? Because this bonded electron is jumping into the conduction band, here one hole is created, here also one hole is created, here also one hole is created. What is the relation in between number of free electrons and number of bonded electrons or number of holes? We are taking the relation between number of holes and we are taking number of free electrons. Can you say number of holes are greater than the number of free electrons? Or can you say number of holes less than the number of free electrons? Or can you say number of holes is equal to number of free electrons? This is correct. Because how many energy levels are there, that many bonded electrons are there. If you increase the temperature, all the bonded electrons will go to the conduction band and creating same number of free electrons, so that here same number of holes will be created. So how many number of holes are there, same number of free electrons are possible. The hole concentration means the number of holes per 1 centimeter cube is represented with P. This is wrong. Is represented with P. And the electron concentration, that means the number of electrons per 1 centimeter cube, is given by N. So these two are same. In case of the intrinsic semiconductor, whether it is silicon or germanium, how many number of free electrons are there? Same number of holes will be available. So N is equal to P we have to take in case of the intrinsic semiconductor. Or when you know that for one particular semiconductor N is equal to P, you can able to treat that one like an intrinsic semiconductor. And this is the reason, very simple logic. When you increase the temperature, all the bonded electrons will go to the conduction band and becoming the free electrons, so same number of holes will be created. So N is equal to P. This transition is called band to band transition. The bonded electrons are moving from valency band to conduction band. That's why it is called band to band transition. Band to band transition. Band to band transition. Okay, like this we have to take. So in case of the intrinsic semiconductor, we have understood that N is equal to P. That means free electron concentration is equal to hole concentration. And we have the formulas for the free electron concentration. N is equal to Nc into e power minus of this Ec minus Ef by kT. And we have a formula for the hole concentration. P is equal to Nv into e power minus of Ef minus Ev by K. If you observe the equation, you are familiar with what is N, what is Ec, what is K, what is T. And in the second equation, you are familiar with what is P and what is Ev and what is K and what is T. K means we did not discuss this one. K is already known thing for you, that is Boltzmann constant. It is just Boltzmann constant. Okay. It is measured in electron volts per degrees Kelvin. Okay. Or it can also be measured in joules per degrees Kelvin. Why? Electron volts can be written in terms of the joules also. So K can be given in terms of the electron volts per degrees Kelvin, or K can be given in terms of the joules per degrees Kelvin also. So anyhow, in the first equation, you know about N, Ec, K and T. T is the temperature in degrees Kelvin. But you don't know about, in the first equation, what is Nc and what is Ef. And in the second equation, you know about what is P and what is Ev and what is K, what is T, but you don't know about what is Nv and what is Ef. So, three unknowns are there here completely: Nc, Nv and Ef. These are the three unknowns are available here. We are going to see them. So, it is the density of states. Density of states related to conduction band, and this Nv is the density of states related to valency band. Then what about this Ef? Ef is a Fermi energy level. Fermi energy level. Okay. So Fermi energy level, to understand about this one, you have to take the energy band diagram. On the y-axis, I am taking energy in electron volts. It is the conduction band. With the lower energy level is Ec. It is the valency band. With the higher energy level is Ev. Then this Fermi energy level will be there in between these two. Or it may be entering into the conduction band sometimes, it may be entering into the valency band sometimes, or it may be available in between this Ev and Ec. So, for the time being, I am drawing like this. Don't consider that this Ef is always available like this only. It is not true. Okay. Ef may not be straight line. Ef may be curve also. Ef can be available in the conduction band also, or nearer to the conduction band also, or it may be nearer to valency band, or it may be entering into the valency band also. To understand about that Fermi energy level Ef, it is one of the energy levels. So many energy levels are there. Okay, on y-axis each value is representing one energy level only. So many energy levels are there. Out of all the energy levels, these Ef is the Fermi energy level. Okay, so about Fermi energy level I am talking now. So Ef is a Fermi energy level Fermi energy level, because electrons are following the Fermi energy level concept. Electrons follow this Fermi energy concept. Electrons are said to be fermions. Electrons are said to be fermions. Okay, and using this concept, what we can tell means, if you take one energy level, in that energy level, electron is available or not available. That is the thing we can able to tell using the concept of the Fermi energy level. And it is actually the probability function. Probability function. Probability function means it is in between 0 and 1 only. Okay. So, if probability function f of E, you see it is a function of energy level. E is the energy level. Okay. It is function of energy or energy level. Changes with respect to energy. Okay. So, any energy level you can able to substitute. By substituting in the formula of the probability function, if you substitute certain amount of the energy, or if you take certain energy level, based on the value you got in between 0 and 1, you can able to think about the availability of the electron. So, availability of the electron means compulsory you should get f of E is equal to 1. It is nothing but probability is equal to 1. So, when you get probability is 1, electron is surely available. It is like sure event in the probability concept. We can tell it is a sure event. So, electron is surely available in the given energy level E. Otherwise, you can take E1. F of E is have the equation. In that equation, in place of the variable E, you need to take E1. If you get your probability is 1, you can able to tell electron is available in that particular energy level E1. If you get in another energy level, you are substituting another energy, so that in that another energy level, if you get probability is 0, probability is 0 means we can tell that is the probability of availability of the electron. This f of E is giving the probability of availability of the electron, because here for the second energy level you got the probability is 0, we can tell electron is not existing in the energy level E2. This is what we can able to tell. But what about the exact expression? I did not give the exact expression till now. It is the probability function. It is equal to 1 by 1 plus e power E minus EF by KT. This is the formula. So, 1 by 1 plus E, all are constants only. E is the variable. When you see the equation, you should understand that what are the variables, what are the constants. So, E is the variable here. Okay, it can be anything. You can able to take any E1, you can take E2, you can take EF also. EF is one of the energy levels only. Okay, and EV you can take, it is the highest energy level of the valency band. EC you can take, that is the lowest energy level of the conduction band. So, any one energy level you can able to substitute. Based on the value of this one, you can able to tell that you can able to estimate the availability of the electron using this probability function. But surely you can tell the value of this one is in between 0 and 1 only. Okay. Now, for our intrinsic semiconductor, we will discuss about this f of E. F of E is equal to 1 by 1 plus e power E minus EF by KT. So, I will discuss this one at temperature 0 degrees Kelvin. Okay, when you take temperature is 0 degrees Kelvin, for different energy levels, if you calculate the probability, what we are getting, so that we can able to draw the energy band diagram for the intrinsic semiconductors. Okay, so I am taking the intrinsic semiconductor band diagram here. Energy in electron volts. This is the conduction band, and this is the valency band, and here certain energy levels are there. You can take this is E1, this is E2, this is E3, or we can tell it is EV, and it is EC, and it is you can take some other energy level like E5, and it is E6, like this certain energy levels I have taken. Okay, so your E can be anything. E is the variable. E is the variable. It can be E1, it can be E2, it can be EV, or it can be EC, or it can be E5, or it can be E6, or it can be EF also. Fermi energy level also. Anything. So what is the formula here? 1 by 1 plus e power e minus ef by kT. Everything is constant except this E. So you can take anything like E. You can take E as E1, E2, EV, EC, E5, E6, EF. Anything you can take. But you are doing this analysis temperature is equal to 0 degrees Kelvin. When you take temperature is equal to 0 degrees Kelvin, how this equation will be modified? F of E is equal to 1 by 1 plus e power E minus EF is in the numerator by 0 we are getting. Okay. So it is equal to 1 by 1 plus e power E minus EF into 1 by 0 is infinity. So here E minus EF is multiplied with infinity. Sometimes this E minus EF can be positive. Sometimes this E minus EF can be negative. So based on the polarity or based on the sign of this E minus EF, here you are getting e power plus infinity or you are getting e power minus infinity. So in which case you will get E minus EF is positive. Positive you will get when you take here E is greater than EF. So for example, this is the EF. This is in between actually this EV and EC. That proof we will do later. You assume that this EF is in between EV and EC at 0 degrees Kelvin. I have taken like that. Okay, we'll see the proof of that one also. So you assume that EF is available in between these two. That means it is EC plus EV by 2 at temperature is equal to 0 degrees Kelvin. Okay, so exactly it is in between these two. That means, for example, it is 4, it is 8, it is 7 electron volts. It is 4 electron volts, it is 10 electron volts. So 10 plus 4 by 2, that is 14 by 2, that means 7 electron volts I have taken. So EF is also fixed. Okay, then, but this E is not fixed. So how I am taking is when E is greater than EF. Two conditions here. We are working under T is equal to 0 degrees Kelvin only. In that, I am taking two subcases. Okay, we are working for T is equal to 0 degrees Kelvin. But one time I will take all the energy levels which are greater than the Fermi energy level. Second time I will take all the energy levels which are less than EF. Third case also you can take if you want, that is energy is exactly equal to E. So when you take energy is greater than EF, what will happen? This E minus EF will be positive because this E is larger than the EF. This E minus EF is positive, so that you will get F of E for this particular case, you will get 1 by 1 plus e power plus infinity. Okay, plus infinity here you will get. So 1 by 1 plus e power plus infinity means it is equal to 1 by 1 plus infinity, that is 0 you will get. Probability is 0 for all the energy levels which are greater than the EF. Probability is 0 means no electron. No electron for E is greater than EF. This is what we got. So in this particular diagram, on the x-axis I will take the probability. That means f of E is available on the x-axis. And what is the range of the probability? 0 to 1. So here 0 I am taking, here 0.5 I am taking, here 1 I am taking. So for all the energy levels which are greater than the EF, greater than the EF means from here to here. From here to here, it is EF, it is greater than EF, it is also greater than EF, it is also greater than EF. So all the energy levels which are greater than the EF, the probability is equal to 0 only we got. That means this is the probability versus energy we have drawn. Okay, all the energy levels are completed which are greater than the EF. Now we will take all the energy levels which are lesser than the EF, we will see this part. Okay, so I am calculating that one here, don't confuse. When E is less than EF, you see carefully this formula. When E is less than EF, this will become negative because this is lower compared to EF. So this is negative means f of E is equal to 1 by 1 plus e power minus infinity will get. So e power minus infinity will give 0. So 1 plus 0 is 1. 1 by 1 is 1. So probability we got 1. That means a electron is existing. Okay, probability 1 means electron is existing. So for all the energy levels which are lower than the EF, so this is EF, lower than the EF means all these energy levels. For all these energy levels, we will get probability is 1. So here we are indicating the probability is 1. On x-axis probability is there. So like this will get. Now if you take E is equal to EF, when your energy level is exactly equal to Fermi energy level. What will you get from this one? When E is equal to EF, this EF minus EF will become 0, E power 0. Otherwise, you substitute here. Okay, you will get 1. So, 1 by 1 plus 1 means 1 by 2 you will get. So, that is a transition actually. It is not a single value. That is a transition from 0 to 1. Sudden change is there. So, this step change you will get here. Okay. So, this is what you can able to take like a energy band diagram for the intrinsic semiconductor at T is equal to 0 degrees Kelvin only. So many conditions are there. It is valid for intrinsic semiconductor. It is valid for T is equal to 0 degrees Kelvin only. This curve is possible for T is equal to 0 degrees Kelvin only. So, what did you understand here? Because for all the energy levels which are lower than the EF, you got the probability is 1. Means all electrons are available in the lower energy level only. All the electrons are available in the valency band only. What did you get here? You checked for the energy levels which are above the EF also. You checked for every energy level. The energy level available in the valency band you have checked, and you have checked for the energy levels which are available in the conduction band also. But you got for the energy levels which are available in the valency band, you got the probability is 1. Probability is 1 means electrons are available in the valency band only when T is equal to 0 degrees Kelvin. So, no current, because if electrons are here, no current. If electrons are here, current is possible. Here, this curve is indicating probability is 0, 0 probability for all the energy levels which are greater than the EF. So, no electron is available in the conduction band. That is what we can able to tell just by observing this particular diagram. This diagram is giving the information that when E is less than EF, probability is 1. That means electrons are available here. Here probability is 0. So, electrons are not available here. That information we are getting from this one. Now, further, we can able to do the same process when temperature is not equal to 0. F of E is equal to 1 by 1 plus E power E minus EF by KT. This is what we have to take. But now temperature you need to take certain 300 degrees Kelvin. For example, room temperature I have taken. Again, the same analysis you have to perform. E is greater than EF. One time you have to do, and E is less than EF. Second time you have to. Okay. So, energy band diagram I am taking in between like this. This is EC, and this is EV, and this is your EF. At T is equal to 0 degrees Kelvin, we got the Fermi level like this, the relation between probability and energy. This side we have the probability 0, 0.5, and it is 1. Here f of E is there, or the probability is available. On the y-axis, as usual, you will get energy in electron volts. This curve is valid for temperature is equal to 0 degrees Kelvin. But now I changed the temperature up to 300 degrees Kelvin. So, to understand now what we need to do in the sense, we will take two energy levels here, E3 and E4, which are above the EF. And below the EF also we will take two energy levels, E1 and E2. Okay. So, first I am taking E is greater than EF. So, see carefully, it is somewhat confusing. So, listen carefully. We are working for non-zero temperature. That means temperature is equal to 300 degrees Kelvin. And I am taking this one into two parts. One is the energy levels which are greater than EF. That means this side. And another case is energy levels which are less than EF. That is this case. And to analyze that one, two energy levels I have taken above the EF and two energy levels I have taken below the EF. That means this case two energy levels E3 and A4, and this case two energy levels E1 and E2. Okay. So, first I am taking E3, otherwise E4 is greater than E3. This is what I have taken. E4 is above of E3. And these two are greater than the EF. Okay, above the EF only. So, I am calculating the probability of E4 in the beginning. That means 1 by 1 plus E power, in place of E I need to write E4 minus EF by KT. KT is existing now, T is equal to 300 degrees Kelvin. So, certain value you will get. Okay. Now, F of E3 also will perform. It is equal to 1 by 1 plus E power E3 minus EF. In place of E, I am writing E3. E3 minus EF by KT. Now, out of these two, which value is larger or which value is smaller? That is what we need to understand. You see carefully, E4 is larger than E3. So, E4 minus EF is larger compared to E3 minus EF. So, this is larger. That means this is also larger. That means this is also larger. That means this is also larger. So, denominator of this one is larger compared to this one. When denominator is larger, total fraction will be smaller. So, f of E4 is smaller compared to f of E3. This is what we can tell. Okay. So, f of E3 must be, that means the probability for this E3 energy level is larger compared to the probability of E4, and probability is available on the x-axis. So, if this is the probability of E4, this must be the probability of E3. Why? We are moving to right side. When you move to right side, probability is increasing. So, the curve is coming like this. And whatever it may be the temperature, when you equate EF is equal to EF, then probability of EF is equal to how much you will get? You see here, E is equal to F means this is 0, E power 0 is 1, 1 plus 1 is 2, 1 by 2 you will get. That means 0.5, exactly it is 0.5. Okay. So, otherwise in the textbooks you will get like this you will get. Same here, smaller probability, here larger probability, and exactly when E is equal to F you will get it is 0.5. Same thing. Okay. So, how you will get in this case? Like this you will get. That means the probability of E2 is larger compared to E1. Here you can able to check that. Same thing. So, to follow this one, I am taking two energy levels, E1 and E2. And out of these two, which one is larger? E1 is larger compared to E2. E1 is larger compared to E2. So, f of E1 is equal to 1 by 1 plus e power E1 minus EF by KT. Similarly, you can take f of E2 is equal to 1 by 1 plus e power E2 minus EF by KT. As E1 is greater compared to E2, it is above of E2. So, this is larger compared to this one. Is it true? These two energy levels are smaller than the EF. So, this fraction will be negative. So, E1 minus EF, this gap is small. So, minus of, for example, it is 2. This E2 minus EF, this gap is large. That means it is like 5, minus 5. It is e power minus 2, it is e power minus 5. Which is smaller, which is larger? E power minus 5 is smaller compared to this one. So, this denominator is smaller, this denominator is larger. Because denominator is larger, total fraction value will be smaller. So, f of E1 is smaller compared to f of E2. That is why you can check in the diagram. The probability here it is, for example, 0.7. Here the probability is 0.8. F of E2 is larger compared to f of E1. So, the curve will be like this. Okay. So, when you take for the intrinsic semiconductor, the energy band diagram, this is EF. So, when you take 0 degrees Kelvin, this is the Fermi level. This is valid for T is equal to 0 degrees Kelvin. But when you increase the temperature, like this is the curve. It passes through 0.5, 0, 0.51, but this is valid for temperature is equal to 300 degrees Kelvin. This is what you need to understand. Okay. This is about intrinsic semiconductor. For the intrinsic semiconductor, we will derive the expression for the EF also. EF for pure or intrinsic semiconductor. For the intrinsic semiconductor or pure semiconductor, we know N is equal to P. Free electron concentration is equal to hole concentration. And we have the expressions for these two, just we need to equate them. N is nothing but Nc into e power minus of Ec minus Ef by Kt, and P is nothing but Nv into e power minus of Ef minus Ec by Kt, because it is related to valency band. So our job is to find EF. So EF is available here, EF is also available here. So take the ratio of NC and NV, and it is equal to, send this exponential to the right side. So e power minus of EF multiply minus inside plus EV, okay, by KT, by, send this one to the right side. So it will be e power minus EC plus EF by KT. It is equal to, send this denominator exponential to the numerator. So you will get e power minus of EF plus EV. As if it is going to the numerator, it will become plus EC, and it is minus EF. This everything is divided with KT. Okay. So here EC plus EV is available and EF is coming 2 times. So it is equal to e power minus 2 times of EF plus EC plus EV. Like this you can write, by KT, and left side here we have NC by NV, and it is equal to, simply we can take natural logarithm on both sides. You will get logarithm of NC by NV. It is equal to, here exponential is there. If you take natural logarithm, this will be cancelled. So right side we will be having with, I'm writing like this, EC plus EV minus 2 EF by KT. This is what we will get. Send this KT to the left side. So you will get EC plus EV minus 2 EF is equal to KT times of ln of NC by NV. NC by NV. Okay. Then we need to write expression for EF. So what will you get? It is equal to write EF expression, EF is equal to, send this one to this side and send this KT term to the left side and divide with 2. So you will get EC plus EV by 2 minus KT by 2 into ln of NC by N. So this is the expression for the Fermi energy level in the intrinsic semiconductor.